So in functional anatomy, we're going to look at basic biomechanical terms, and we use biomechanics to help us analyze the movements that we're looking at, and this helps us kind of reverse engineer which tissues are involved, what joints are responding, and what's required from us from an intervention perspective. So when we look at the types of movements, and we're borrowing a lot from physics, there's two basic forms of motion. There's linear motion, this is also referred to as translational motion, and angular motion, also referred to as rotational motion. Just recall that there's 360 degrees in a circle, and there's a fixed axis of rotation. Most of the movement that we are going to deal with is what's called general motion, which is a fancy way of saying a mix of both. So we're looking at simultaneously linear and angular motion. We deal with both, and there's others in physics, but we're going to look at these two because this is what we're dealing with from a sports performance or from an injury rehab perspective. So when we look at translational movement, what makes translational movement distinct from rotational is that there's a starting point, like here, and an end point. It doesn't mean that the path has to be straight. It can curve in a curvilinear fashion, but there's a distinct starting point and a distinct end point. When we compare that to rotational movement, there's a mass or a body moving around or rotating around a fixed axis. So there's not as a starting point or an end point. It's continuous. Now, when we deal with the human body, we're dealing with joints and angles. There is a limit to what we can do. You can't do full 360 degrees, but you're going to do some angle in between 0 to 180 if you're looking at the shoulder, or 0 to 120 if you're looking at the knee, and everyone's going to vary a little bit. But the primary aspect is there's a fixed axis of rotation. Now, the axis itself may not stay stable. So if I was able to show, I would take the screen and I can move this up and to the right or down to the left. So the axis can move through space, but the mass that's connected to this is rotating around this fixed axis. Now, when we look at human movement is a combination of both. We typically, most of our joints that we deal with in this class or in our nature of working with the human body, there's rotation. Some joints can go through a gliding motion or shearing force, and all these joints have that capability, but we're looking at rotational inputs. So we're looking at like the shoulder and the elbow or the wrist, and based on these rotational inputs, we are producing linear output. So when you look at the majority of sports or exercise, you're either pushing things in a linear path, you're throwing a football, you're kicking a soccer ball, you're running, you're jumping, you're pushing a barbell or dumbbell. And so all of these have linear paths that we are following. So even though our output is linear, so in this case you have the two segments of the body reaching for this glass, this was produced by rotation of the shoulder, rotation of the elbow, and rotating these segments to produce this, what we perceive as a smooth linear output. So we get into this question, what's causing this motion or what's causing this movement? And it's not a rhetorical question. We really want to consider, how is this happening? When you think about the skeleton, this is where movement's occurring, this is passive tissue. It does not have the ability to excite. It doesn't have the ability to change rapidly. So where is this motion coming from? The physics answer from a biomechanics perspective is force. And if you recall from your physics or from just basic science, a force is a push or a pull. It's exerted both internally, and when we look at internal, this is coming solely from the neuromuscular system. And when we look at it externally, this can come from other sources of resistance, but we're mostly dealing with the force of gravity. So when you're trying to control your own body weight, you're trying to lift a barbell, a dumbbell, you're trying to throw a sandbag or a sports implement or a football, these are all under the effects of gravity. And really what we're doing is this is an ongoing battle between the internal forces of muscular tension and the external forces of gravity. Now I'm just going to back up one slide here. That gravity is our primary external force, but when you think of resistance and resistance exercise, we have elastics, which is independent of mass or gravity. It's based on tension, and so it in itself kind of matches the internal muscular force, which is tension generated. And the other type of resistance that we normally encounter is some kind of pneumatic or water or wind resistance. And this is dealing with like aquatics in the pool or some kind of pneumatic aspect. But those are your primary resistances that you're going to deal with. And like I said, 90 to 99% of what you're dealing with is going to be gravity. I do want to point to your attention, and we'll get to this in another lecture, is that muscles, the only thing they do is generate tension. That's the only force they produce, and they always pull, they never push. So muscles always pull, never push from this perspective. So we have this push-pull relationship, this gravity. And when we look at muscles, when they produce tension, they're pulling, they actually are more inverted in this aspect, where they're coming from the center and they're pulling from the sides, and they're usually pulling on bone. So it's the tension that's being generated. So when these forces are acting upon an object, they can act upon it either at its centric point or centric aspect, the center of mass, which we'll talk about in another slide actually coming up. And basically, the center of mass is a theoretical balance point. If the force of gravity is affecting an entire object, it's acting solely through that one point. It's acting through the entire body, but mathematically and figuratively, it's acting through that mass. So what you're seeing here in these three different examples in A, B, and C is you're seeing a force, a pushing force, being directed right through the center of mass. And what ends up happening is it moves the object in a likewise fashion. If I push this way, it's going to go up, and if I push at an angle, it's going to follow that angle. If I directed force outside its center, eccentric, right? And if you think of and these are not the same as concentric contraction or eccentric contraction. These are different. This is talking about forces. But if someone's eccentric, they're off a little bit. They're not quite normal. They're unique. And in this aspect, if we apply these same forces and it's not through that center of mass, you're going to end up with a rotation of the object. And if we add multiple forces to it, like we see here on the right, we get to what's called a force couple, where you have one force directed in one direction, another force linearly directed in an opposite direction. So linearly, these forces should be opposing each other. If they were the same, they would cancel each other out. But since they are off-center, they are working in concert with each other synergistically to create a rotation. And when we start looking at the different upper extremities, lower extremities, joint responses, we find that a lot of our musculature is paired in these force couples to get this synergistic type effect. Now, forces can be compound, like I said, where if you have opposing forces, but even if you have forces that aren't opposing, what's unique about force, it's a vector, and so they add to each other. And I don't know if you remember the tip to tail aspect, but if this guy is pushing this direction, this guy is pushing that direction, their work is being compounded, and we would end up with a resultant angle in this direction here. So this is the direction in which this object would go given a frictionless surface or any of the other environmental constraints. Now, if this guy starts pushing more, that's going to skew this angle. It's going to skew this angle up this direction. And if this guy's pushing more, it's going to skew it this direction. And the reason why this is really important, it's not just theoretical biomechanics stuff, is that when you are determining which muscles are participating in a particular movement, or which muscles are being stressed or which tissues are being worked in an exercise, you need to understand how muscles contribute. There's a lot of myths that are propagated through the fitness industry and rehab industry that you can isolate certain muscle function, that, like, for the one example that comes to mind, which is a direct application of this principle, is the decline bench press. And a lot of people think that decline bench press works the lower pecs and the incline bench press works the upper pecs. And this is not true. The decline press works the lower fibers of the pectoralis major, but it also recruits the upper fibers as well. And it's based on how much of the muscle fiber is contributing to its output. So you might be linearly moving in this direction, and you will have a resultant force. Let's say this is the direction you want to move. You want to move from left to right. This guy, even though he's pushing this way, he has some contribution to that aspect, especially if he's angled a little bit. Just because a fiber isn't in the exact line of pull doesn't mean the body's not using it. And just because the fiber might be at a slight angle or not contributing a lot to the angle of that direction, it doesn't mean it's generating tension as much as it can. So that's the false aspect, is understanding these resulting vectors, the resultant vectors. You have a better idea of how muscles are participating, who's participating. The example I have here in the slide is the deltoid complex. And a lot of times the anterior deltoid would be labeled as a shoulder flexor, and the posterior deltoid would be labeled as a shoulder extensor, and rightfully so. So if you can see my laser pointer there, that would be the axis of rotation, and the fibers on this side would be contributing this direction, and these guys are going to contribute that direction. And then the middle deltoid is considered the one that does abduction, so lifting your arm out to the side. But when you look at the resultant force here is when the body is initiating or recruiting the anterior deltoid and the posterior deltoid, the resultant force is directed out this way. And so all three heads of the deltoid do lateral flexion, bringing your arm out to the side like a delt raise if you're familiar with exercise. We will get more into that in each respective body part. So the internal forces are generated by muscle tension. They're pulling only, and we'll talk more about this in the muscle unit when we look at contraction. But it's an attempt to pull both ends together. This is an attempt to shorten. And these arrows you see here are the resultant vectors of that. And just quick introduction, and we'll talk about it more, is that the muscular contractions of eccentric contraction, concentric, and isometric talk about the resulting joint output. But the key thing in all three of these contractions is that muscle tension, internal force, is being generated. So when we look with external, when we're dealing with external forces, like I said earlier, we're normally dealing with the force of gravity. The force of gravity is always down. It's always pulling objects down towards the earth. It pulls the same on all objects. When we're dealing with external forces, like I said earlier, we're normally dealing with the force of gravity. Gravity is always pulling down towards the earth. And so when we're analyzing the direction, or you're trying to match the movement with the force to create appropriate resistance exercise, gravity is always down, never changes. Pulls the same on all objects. So a 5-pound dumbbell and a 500-pound dumbbell have the same force of gravity. They just have a different weight because of the amount of mass that they have. We have machines available to us. So when we look at like cables and we look at the machines that are on the gym floor and in the clinic, even though the direction might be different in terms of the way that the cable is being angled, the resistance is still gravity. It's just being on the force, the weight stack here. Gravity is still pulling this down and you're still pulling up. Just the pulleys may redirect. Depending upon how many pulleys you have set up or what kind of machine or leverage system you have, the weight that you're pulling might be more or less based on how the machine is doing the work. So like I said, we're normally dealing with this internal versus external battle. And when you are trying to move, your body is trying to move in space at these axes of rotation, producing rotational movement, and your limb is under the effect and your body's under the effect of gravity. And the reason why you're not collapsed over in a hump of meat is that you have muscles that are pulling on bones that are generating tension to overcome gravity. And so it's this constant aspect of overcoming gravity that becomes theme in exercise selection and exercise creation and therapeutic interventions. So as I said with the 5-pound versus the 500-pound dumbbell, is that what gives weight or what gives weight resistance is not how much gravity is pulling on that. That's constant. That's 9.8 meters per second. But the gravity itself is what's different is the mass that exists in that object. So in this case, it's looking at how you would be if you were on different gravitational environments, which doesn't happen here on Earth. There might be some fluctuations in gravitational pull, but negligible resistance. But what's happening is gravity is pulling at a constant speed. And as we mentioned earlier with this center of mass, gravity equally on all parts of the object, and that can be calculated down to one center point. In terms of physics, if you're an astrophysicist or you were a person of exactness, there is a difference between the center of mass and the center of gravity. They are the same in the same gravitational field which we are in. So for our purposes in this class, for when you're doing any kind of body analysis, as long as you're not in space and not in Mars and not on the moon, which is possible but unlikely, you're going to be on this planet Earth doing exercise and intervention and so forth, center of mass and center of gravity are the same. And like I said, it's the theoretical balance point that exists. The reason why this is important is that when we start to look at why we're able to stand upright or why we're not falling over, or this concept of stability. Stability is basically you have this base of support that is made with the contact on the ground. So in this case, this woman standing here, she's standing here, her footprints are here, and her feet are the border for her base of support. And this red line here represents this straight line down, effective gravity through that base of support. As her center of mass changes based on her bending or putting the limb out to the side, so does the center of mass. So the center of mass isn't static, it's based on the environmental constraints. If she leans to her left, it's going to move over her left foot. If she picks her foot up, she's going to have to shift her mass because her base of support is going to go from here to just this right here. And if this center of mass line ever comes outside of her base of support, that is the definition of instability, and a fall is imminent because the body either has to recapture that center of mass, something has to change. If she bends forward, it comes forward. So you can see that when we look at how we're bending, how we're moving, what we're doing, our foot placement, how we stagger our stance, this all affects our base of support and this center of mass. And the goal is to try to keep that within center when you can. So you can see in these different examples here of how contorting the body can affect the center of mass and what the center of mass is doing. If it's outside of the bounds of the base of support, you're unstable. So you have to make some kind of correction. You either have to take a step to capture the base of support again, capture the center of mass within the base of support. You have to stick a leg out to the side or arm out to the side or bend to move your center of mass back within the constraints of your base of support. So if you think about you leaning to your left too much, you're going to fall left. What you normally do is you'll stick out your right leg to try to move more of your center of mass back to the right so that it moves this center of gravity back within that base of support. So there's 5 things that determine stability. And the one I already kind of alluded to was the size of the base of support. But some of the things are within our control, some of the things are not. So the number one is the body mass. So the more massive an object, the less likely it is to fall over. This has to do with the amount of contact on the ground, so it's indirectly related to friction. The more friction that you have between the two surfaces, the more stable an object is. The alteration of the base of support. So you can spread your legs apart, you can put your legs together, you can stand on one foot, you can go down into a 3-point stance here, or you can put your hands a 4-point stance. And in the end, the bigger the base of support, the more stable you have to be. In order to be knocked over, this center of mass has to come outside of that base of support. So in class, I'll ask, what is the most stable position you can get into? And if you envision laying on the ground making a snow angel, that is your most stable position. That's the hardest for you to be knocked over. Some would say that you're already on the ground. The next thing is manipulating your body of mass to anticipate impacts or falls. So if you're a skier or an ice skater or a football player here, what they might do sometimes is purposely lean to the left to throw their center of mass. Let's say their center of mass is here, anticipating an external force from a defender coming in, and that hit knocks them back to balance. Whereas if they were here, this amount of force here might knock them off their feet this way. But what the athlete did was lean into it, anticipating that to hit that center of mass. And the one that's probably the most applicable to what we can control almost immediately is the height of that center of mass. And what that means is that when you have a higher center of mass, a taller object, the force will have a bigger moment arm or bigger lever. And we'll talk about levers in the next lecture. But if you can, let's say, squat down and lower your center of mass, you'll give the opponent a less of a lever to knock you over. So the wider your legs are, the closer you are to the ground, the harder it is for you to fall over, for you, your client, or your patient. And this image here depicts that. Whereas the center of mass here and a small base of support, dropping down, widening the stance, you make it harder for you to fall over. From an exercise perspective, or from a progressions aspect, you can manipulate stability both by the surfaces, right? You can either be a stable surface, or it's very popular now for these liable surfaces with like Airex pads and balance boards and foam and these type of things to challenge. But if you wanted to challenge stability, the most likely progression is to first manipulate these points of contact on the ground. Like a seated position is going to be your supine position, laying down is going to be the most stable. Then a seated position. then a wide staggered stance, and then a wide or narrow staggered stance, and then a wide regular stance, and then you get to single leg activity. And I would exhaust all of those first before I start to play around with these liable surfaces. But just give you examples to help out. So that's basic biomechanics. I would still read through your chapters for any more details, but these are the most applicable things that we'll be using through functional anatomy.